Uh, my name is Suman Itani. I'm a PhD student at University of New Hampshire here. I'm working with Jialing Chang. Today, I'm going to discuss about how large language model can be used to accelerate the discovery of new functional materials. I think in our very first talk yesterday, Professor Yuna already talked about this empirical data analysis part, and today our Professor Shaoling already explained more detail about the large language model. So, uh, so in general, we have four paradigm of research: experimental theory, computational driven, and the AI driven paradigm. We are doing research in this fourth paradigm, which is AI driven. Here we need some data, and we make some prediction model on the basis of this data, and we'll predict this. We'll use to predict the material properties using this model we built. And the main goal of this project is to accelerate the discovery of the magnetic materials, especially the alternative permanent magnet candidate and the superconductor. Is there any new family of superconductor we can access through this approach? So the question is this data enough, the current data enough to do this kind of research? Unfortunately, it's not enough. So currently we have this kind of database, the material project, which is a DFT generated database, and it contains around 170,000 compounds, but this is DFT verified. This is not an experimental one. So the magnetic information it contains is not trustworthy. Some magnetic properties calculated through the DFT are not trustworthy. So we are looking for the magnetic material database which is experimentally synthesized. And this, we also have Bilbao crystallographic pseudo database, which is small, but this is good news. It's experimentally verified, but it contains a small or few number of properties info. And for the superconductor, we are also doing something on the superconductor. We have supercon database, which is experimentally synthesized database with 18,000 compounds, but this database also does not contain any structured information. So we are looking for building a database for these kind of compound like magnetic materials or a superconductor. And the problem is where is this kind of database and how we can extract this kind of information. So the answer is there are so many literature, thousands of literature contains so many important empirical data experimentally synthesized. So the problem is we cannot manually extract this kind of data from that paper. So we came up with a simple but powerful idea. So we want to use this large language model for the data collection, and later we can also use this large language model to predict the material properties. So this large language model is an advanced system trained over the vast text data, and they can understand and generate human-like language, including reading or summarizing the scientific article. So we want the data in this format because we want the data like the material composition. We also want some temperature information like transition temperature, Curie temperature, Neel temperature, Curie Weiss, or structural information like crystal structure, space group, lattice constant, or the magnetic properties like coercivity, remnants, magnetization, or the magnetocrystalline anisotropy, which are very important for the permanent magnet. And we also want to know that this paper is experimental or DFT. So these are the key properties we want from that papers. So this is the workflow we develop here. So you can see the scientific article, we start from the scientific article. So not all the journals have the same way to access the article in a high volume. Some allow to download the paper in the API, some allow to download in the PDF format. So, or we also have some sort of old papers which is not in a regular PDF form, which is just a scan-based PDF. So we need a multiple approach to deal with this kind of papers. So first of all, we access the paper in API format, through the API in XML format, and this XML is not a clean format. It contains unnecessary tag, and the character we should need to make it clean, and we just decrease the token inside that papers, and we just develop the text parser and the table parser to just convert this XML format of data to the plain text format. And then we also deal with the PDF, like the PDF parser. This PDF parser convert this PDF format to the text format, clean text format. And the challenge here is we have a very old papers, which is in the scanned image format, and it's very difficult to convert these things to a regular text file. So we use the powerful Gemini OCR technique. OCR technique can scan the text in that image and just give you the regular text-like format. And after getting this all document in a clean text format, we just pass this text to the large language model along with the prompt. And this prompt can handle this paper, what are the information we are looking for, and this gives us the output format like this, and we use this output format to build a database. And the main things here is what kind of prompt we use to extract this kind of data. So LLM are powerful, but how you interact matters. So sometimes your prompt doesn't give you a good output. So you need to have very clear about the prompts. So we use this kind of prompt. We first describe the task description, like what are the main things this large language model should do. We just tell them the specific detail for each magnetic materials or superconductor mentioned in the research article, focusing on the chemical composition, magnetic transition temperature, or other information what you need. And it should be organized in JSON format, because if the output doesn't give you in the JSON format, it's very difficult to handle this format later. So after this task description, in an overall task description, we have to just give some instruction about the large language model. So first of all the papers we pass are not relevant. Sometimes we pass the not relevant paper, like we are looking for the superconductor database, but sometimes the paper are not relevant to a superconductor. At the time, the model directly know about reading the few lines of the paper, and it will generate the output nothing. So we just, for that things, we just give this kind of prompt determine the relevance of that papers. And then if that paper is relevant, then we also give a further extraction information. The model should focus on this introduction part, result and discussion part, and conclusion section of the paper, not on the methodology section. And then later, for each material composition mentioned in the paper, sometimes the paper contains so many material composition. So there are so many materials discussed in that paper, so the model should output each materials with separate JSON, so that we can extract these things later for the database purpose. And if the information is not available, sometimes not all information are provided in the paper. So we just tell the model, do not infer or guess this kind of information through the pre-training. So we also need to inform these models in that way. And for the other properties like chemical composition, sometimes the chemical composition is just mentioned in the variable form, like the stoichiometry is given in the X. So sometimes model just give you the stoichiometry in this X format. So, but we need to tell the model that, oh no, you have to look for this value of X in somewhere in the paper where that mentioned this value of X. So in that way, the paper, the model give us the clean chemical composition from that paper. So we can also implement the same kind of prompt for other properties, but the important thing here is we need the output in a very uniform form. So there is one technique in this prompt engineering. So this is one-shot prompting. You have to tell the model what kind of output you are looking for. So for example, we are looking for this kind of structured output. So we need to pass the model this at least one example. So we call this the one-shot prompting, and then the model will always generate this kind of output. So in this way, we build 3 different databases: a magnetic material database, superconductor database, and the thermoelectric material database. And this is the magnetic material database, which is the, I think, largest database, experimentally made database at this point. And for the superconductor, I think we only uploaded here 19K data, but we have almost more than 40,000 data entry for the superconductor also. So this is our website. We just make this database publicly available, and you can use your machine learning model to this experimentally verified data. And the performance, the accuracy of this database is more than 95% for each key, separate key accuracy. And for the application part, we also build some machine learning model, which is simple, but on the basis of this database, we just build a classification model, which is just here you can see the confusion matrix. The diagonal lines show you the correct prediction by our model, and the off diagonal line are the just incorrect prediction by our model, which is 91% accurate. And we also build a machine learning model, which is XGBoost or the simple neural network to predict the Curie temperature of the ferromagnetic compound, and which is 0.87 with R2 value, and mean absolute error is 56 Kelvin. And using these two different prediction model, we just implement this model to the material project, and we just identify some compound which has a Curie temperature greater than 500 Kelvin. And these out of these 32 high TC ferromagnetic compound, 7 are just rediscovered. So we found later that, oh, these 7 compounds are already measured the experimental value, and that also matches nearby. And we also calculated the DFT TC through DFT for few compounds like this. You can see here the predicted value and the DFT predicted value is somehow match for each. Both prediction has Curie temperature greater than 500 Kelvin, and we thought that our model is at least can identify some high TC compound. And we have a plan to implement these kind of things for other properties also, like magnetization and magnetocrystalline anisotropy, other properties. And the next application of this large language model is not only for the database application, creation of database application, we can also use this large language model for the property prediction by fine tuning. So the general purpose model like GPT-4o is just a general purpose model. We can use that, we can make this model more effective or powerful for one particular task by fine-tuning. So fine-tuning can be done through different ways. We can fine-tune the large language model by full parameter fine-tuning, or we can also fine-tune the large language model by a small portion of the weight to be fine-tuned. So there is a smart way to do this kind of things even in the small GPU. So there is a low-rank technique, so low-rank adaptation technique. So we need to change this W0 parameter if we want to fine-tune the full parameter. But we can just make this W0 frozen. The original parameter is frozen, but if we add some adaptation layer AB, which is just matrix decomposition, if you multiply matrix A and B, which is small rank matrix, this gives you the same size of the matrix with W0. So that means you don't need to change the parameters. You can just change the parameter of the model with the small total parameter changing. I mean, if you change this W, you can change the whole parameter of the things, and the model will be smart enough for the particular task. So we are just using this kind of a parameter efficient model to fine-tune some small model, a large language model. So we've just fine-tuned the Mistral 7 billion parameter model. So we just make this kind of a data set from our database. So we just give an instruction for the superconductor, predict the transition temperature from the given crystal structure and composition. We just give the input, material composition, structural information with complete SIF information, and the output is the transition temperature. And you can see here before the fine-tuning, the model performance is like this. The left-hand side is just the before fine-tuning, the same model, and the right one is after fine-tuning. You can see the R2 value is improved from 0.046 to 0.728. And I think this is a small parameter model, so we can fine-tune the even bigger publicly available bigger parameter models, and we can see the even better performance. But the problem is we need to have a better GPU than we are using right now. And this is the another base model we fine-tune. This is a Llama 8 billion model, and this is also learning something from fine-tuning. So I think we can hope that we can use this large language model to predict the material properties also. And in summary, I can just say we developed this large language model-driven workflow to extract the structured data from scientific literature. And the important thing here is we can implement this technique to collect any kind of information. Just change the prompt. You don't need to deal with other things. If you change the prompt, you can implement this technique to any kind of data collection process through the literature. And we also build a database for magnetic materials, superconductor, and thermoelectric using this workflow. And we also build a first scientific analysis, like some few prediction model using this data, and we also demonstrate the potential of fine-tune large language model for property prediction and especially inverse design in the future. So we are planning to fine-tune this model for especially the inverse design problems, just giving the properties information to the model and ask the what kind of material has this kind of properties. So this is a very difficult task in material science, this inverse design. So we are optimistic that we can at least fine-tune some model to get this kind of inverse design problem solution. And I can just acknowledge my professor and my postdoc. Thank you for your attention. Thank you.
What kind of quality control do you have for entries that are being scraped from papers into your data? Like, how do you prevent entries from, say, like, it detects a magnetic material, but it knows nothing about it, so it just puts the name?
So you mean what kind of information we just collect?
Well, you're generating quite a large database, and you're scraping like a large amount of data. So how do you protect the quality of that database from having, important information only or having any information at all? Do you do any quality control when you use data collection? It's not much.
So we don't use any quality control. We just try a different prompt to see the performance. So we use we just use so many prompts, and we just first we just see the performance of the model first. So how the model interact with that prompt, and later the best performing prompt, we use this prompt later, and we also validate our database through manually and the second large language model also. So we just utilize this large language model GPT-4o to extract this information. So later we use the Gemini, another large language model, to read the papers through that. Just this is right or wrong. So we just tell the large language model, just try to see this information extracted from this paper through here is available in that paper or not. And I think from that approach also we get the similar kind of accuracy we manually did for the 500 papers. So it's not possible to read the all papers manually, so we just do this kind of stuff to just see the extracted information quality. Yeah. Mm-hmm.
So that's the next thought. So one question I have is, so for magnets, when you're deriving Curie temperature, you said like you do that from 2 feet. So like, how do you precisely do that? Like, what are the steps? Like, what are the errors? Like, DFT might not be tested.
So I think I cannot answer that question because these kind of things I don't through our postdoc. So I don't have that much information for the DFT part. So I'm sorry. Yeah, for the DFT.
Thanks for the question, and thanks to the in respect of time, let's move to the next speaker. Thank you.
Thank you.